Hello everybody. So today we'll move on to section 4, molecular shapes. So before we move on, I would like to talk about a little bit about this practice. It's really the foundation for because electron dot diagram is really the foundation for molecular shapes. So I can talk about a little bit about this practice. It's quite if you guys forgot or still confusing how to figure out electron dot diagram, so we can know a little bit better. So first thing, you need to figure out which one is a central atom in those cases, right? So the central atom. So for example, there's a phosphorus trichloride. So you need to compare which one is check periodic table, figure out which one is a central atom. So in periodic table, just phosphorus, chlorine. So phosphorus is the left-hand side. So phosphorus is central atom. So we have central atom, then we have terminal atom. This means terminal should be around the central atom. So if you have something like that, right? So if you draw a structure like that, both phosphorus and chlorine are going to be central atom. So central atom has to be central, and terminal, outside. It cannot be like linear, because this chlorine is going to be at a central, not terminal. So this is totally wrong. So central at the center, that's why it's called central. And terminal is going to be around the central atom. So it's going to be 3D, not linear. Right? So in this case, phosphorus is central, and the chlorine going to be the terminal. So that's why it's going to be layout going to be something like that. Then you figure out what kind of bonds. So we have two ways. One is figure out the total number of valence electrons. Chlorine has 7 valence electrons. Phosphorus have 5 valence electrons, but we have 3 chlorine, right? There's 3 chlorine, so multiply by 3, so it's 21. Total is 21 valence electron plus 5. So add 5, figure out total is 26 valence electrons. And for both phosphorus and chlorine need 8 electrons. That's why we talk about octet, right? So octet each need 8, and total have 4. So 1 plus 3, total is 4. So 4 multiplied by, so it's 32. So this is the second method we talk about. We have 26 electrons, but we need 32. So the difference is 32 minus 26, right? The difference is 6. So we need to have 6 electrons shared between phosphorus and chlorine. So this each bond is 2 electrons. So we have 2, 4, 6 electrons. You draw 3 lines, all single bonds. There's 6 electrons. Right? We have 26 valence electrons, and we use 6, already put 6 over there, minus 6, we have 20 electrons left. So we need to put this 20 electrons. We start with terminal, put a lone pair electrons around terminal first, right? 2, 4, 6, 7, 8, 10, 12, 14, 16, 18, right? So the total 18. So this one minus 18, we have 2 electrons left. So we need to put the extra 2 electrons on the central atom, right? Then the last step, we need to check octet. So we check terminal chlorine 2468. That's all same, 2468. So it's 8 electrons, satisfy octet. We check the central phosphorus. So 2468, 8 electrons, right? So both terminal and central have 8 electrons. So this should be the structure, Lewis electron dot structure for phosphorus trichloride. So next one is hydrogen peroxide. Same thing, we talk about hydrogen always terminal. So let's see there. So oxygen is central, put oxygen in the center. And the hydrogen can put around, hydrogen around the terminal. That's why I call it terminal. Outside central oxygen, the central is called central atom. That's why we talk about central and terminal. Because in some of your guys' practice, you put like linear, something like that, right? So both hydrogen and oxygen are going to be central. That central means it is surrounded by some atoms. That's totally wrong. Because only oxygen is central. That's why we talk about central and terminal, central, terminal so many times. So in this hydrogen always terminal, we talk about several times. If you forgot, review the section 3 notes or review the video. Right, then we figure out how many electrons we have. So oxygen, we need we have 2 oxygen. Each oxygen has 6 valence electrons, multiplied by 2, 12 electrons. Hydrogen, we have 2 hydrogen. So each hydrogen has 1 electron, multiplied by 2, we have 2 valence electrons. So total, we add up this total, 14 valence electrons. Right? So then we can start to put this then second step, we figure out how many electrons we need to satisfy octet for all the atoms. So oxygen need 8. We have 2 oxygen, right? So we need 16 electrons. Hydrogen, each hydrogen only need 2 electrons to satisfy octet, not 8. Hydrogen exception. We need 4 electrons. And add up total, we need 20 electrons. So the difference between these two numbers, 20 and 14, so the difference 20 minus 14 have 6 electrons. So we have 3 bonds, 3 pairs, because each bond is 2 electrons. So 6 electrons we need to share, and 3 pairs. So in this 3 pairs, so we can draw this way, this way, this way, 1, 2, 3. We have 3 bonds, right? 3 bonds, 3 pairs, 6 electrons. This is based on our calculation. Because why link like that, but not this way? Because both oxygen and central atom, it has to. So central atom means it at least has 2 bonds linked to it. So if you draw it this way, so this one become terminal. That's not right. This oxygen is central too. So you need to have at least 2 bonds linked to both oxygen. That's why we call it central atom. So something like that. So you can draw it a little bit better way. Right? So we calculate we need 20 electrons we have. So this is what we have. This is what we need. we need 20, we have 14. So we already put 6 over there. If it's minus 6, we have 8 electrons. We need to put around central terminal first. Because hydrogen only needs 2 electrons. So this hydrogen already have 2 electrons. So we can put no more on hydrogen, only on oxygen. So all 8 electrons need to be around oxygen. So we put around oxygen. 2, 4, 6, 8. Right? The last step, we check octet. So check the hydrogen already have 2, so it's good. So oxygen, let me check oxygen. It's 2, 4, 6, 8. So it's 8. Same thing for this oxygen, 2, 4, 6, 8. It's 8 electron. So all the atoms have satisfy octet. So this one is a structure for hydrogen peroxide. Right, same thing, I'm not going to do the step by step. I just give you the structure for next to save some time. If you still don't know how to figure out, just let me know. I'll show you how to do those last two. So this one, something like that. Right. So last one has 2 possibilities. This is one possibility. Another is all carbon is central. Right. So if you check octet, it's all the atoms satisfy octet. So last one, this one has 2 possibilities, 2 possible structures. This here's one possible structure. This is another one. One is a cyclic, all the carbon in form a circle. The other one is linear. Right? Let me know if you have a question for last two. So then let's move on to the next section, molecular shapes. So this molecular shapes really depend on the electron dot diagram. So if you still have problem for section 3, you really need to review the section 3 notes and the video. Right, so we'll talk about a few things. One is what's called this initial 5 words whisper bond theory. What's whisper bond theory? We'll talk about this. And we use this theory to predict the shape of a molecule. And the shape of molecule, so this theory kind of related to the hybridization theory. So this two theory we talk about, whisper model and hybridization theory. Right, so the shape of molecule really determine the physical chemical properties, but we are not going to talk about the relationship between the shape and physical chemical properties, but you need to know the shape of molecule is very important. Right, the 3D geometry, the shape also called geometry. We can use this called whisper model. It's called valence shell electron pair repulsion model. called the whisper model, valence shell electron. So that's why that's what we talk. We're going to focus on. We'll only focus on the valence electron because the valence electron really determine the 3D geometry. So basic the basic requirement is just minimize the repulsion between electrons. Because electron, we know electron is a negative charge, right? So the negative charge is a negative charge going to have a repulsion between each other. So that's the foundation of a whisper model, because it's a repulsion interaction between the electrons. We know this outer bond, like hydrogen-hydrogen bond, is two electrons, basically share of two electrons. Because if we have another bond, just bad example, water, right? Basically, each bond two electrons. So those electrons going to repel each other. So basically, these two bonds are going to repel each other. So that's the foundation for the whisper model. So electron pairs repel each other. Basically, chemical bonds are going to repel each other. Those unshared electrons, remember we talked about, like on this oxygen, it's two lone pair electrons. It's two lone pair electrons. So also electrons, basically. So electron going to, those lone pair going to repel with repel those bonding electrons, also repel this another lone pair. So basically, all the electrons going to repel each other. So no matter it's shared or unshared, they'll also all of them are going to determine, have a, involved in the determination of a 3D geometry of a molecule. So the rule is the electron pairs, basically all the bonds, all the lone pair are going to try to go as far as possible to try to minimize the interaction between the electrons. So that's the foundation for the whisper model. Right, there's some examples, sample typical geometry or shape of molecule. First one is very popular shape called a tetrahedral. So tetra means four, hedral means faces. So it's four faces, kind of like this, because if you draw this bottom, this is called a ball stick model. So those balls, all those balls atom. The stick is just some chemical bond. So if you draw this bottom three atom like a triangle, so this one on top actually, this so just a four face of this each of this 3D structure, four faces, each face a triangle. So that's why I call it tetrahedral. Four faces, one, two, bottom, and on the back there, four faces, tetrahedral. So bond angle is this angle between each bond. This one is 100 between any two bond. Any two bond is 109.5 degree. So it's something kind of pyramid with a triangle base. So if you think about this, the bottom as a triangle, top like a pyramid. So in this structure, the central, there's another atom at central. So it's 5 atoms. So it's basically one central atom, 4 terminal atom in this case. So all the structure like this, methane or natural gas, majority of the component natural gas, or anything of those with 4 terminal atom is 1 central atom, something like with a tetrahedral structure. 1 central atom with 4 terminal atom has tetrahedral structure, right? So basically, you look at a formula. 1 atom with another 4, basically something like that, going to have a tetrahedral structure. Right. So next one kind of is derived from a tetrahedral structure. So it's based on tetrahedral structure. However, because so in this structure, this yellowish ball is a lone pair. It's a lone pair. 2 electrons. 2 lone pair electrons. There's no atom there. So only this what? Right? So only this 1, 2, 3, 4 I label as 4 items. On top is a lone pair. It's not atom. Lone pair on top, because lone pair electron is not bonded. So lone pair take more space, so it has stronger repulsion. So lone pair gonna repel all the bonds harder, kind of. So it kind of squeeze the bottom structure, kind of little bit squeeze. So top has more space, bottom kind of squeezed together a little bit. So the shape, actually, when we talk about the structure for molecule, we don't talk about this lone pair, because lone pair is not atom. When we talk about the shape of molecule, we talk about all the atoms form the shape of molecule. Lone pair is a determining factor, but it's not going to show up in the shape because it's not atom. So the shape going to be something like that. So this is the shape of molecule. There's no lone pair. Forget about lone pair when I talk about the shape. So it's called a trigonal pyramidal. So the bottom is a triangle. However, the central atom is not on this plane. It's kind of goes up. So basically, you have a triangle at the bottom. So that this central atom gonna on top. The bond, all 3 bonds. So all 3 bonds not on this bottom triangle. It's on top of this bottom triangle. So this is the structure, the shape. We'll have a virtual lab. You can play around with 3D structure of all those shapes. You'll probably have a better understanding. So in this case, remember we talked about when we talk for the perfect tetrahedral, the bond angle is 109.5 degree. But because of this lone pair stronger repulsion, so this angle become larger. This angle become larger than 109.5 degree. So the bottom, this angle becomes smaller. So it become 107.3. You don't need to memorize this bond angle. You just need to know, because a lone pair take more space, you need to know this. So this bond angle is smaller than a perfect tetrahedral, which is 109.5 degree. Example, something like ammonium, phosphorus, trichloride, all those has a trigonal pyramidal structure. Right? So next one is further derived a little bit further from tetrahedral and pyramidal, a trigonal pyramidal. Now this case has two lone pair, so there's two lone pair there. Typical, this example is water. Oxygen is two lone pair. However, the two lone pair are going to take space, so water not going to be a straight linear. Water is not linear, so water is going to be so water is not going to be linear, going to be band structure. So this bond is not linear, going to be band, going to be here. Because it's two lone pair on oxygen. So this foundation, if we draw the structure of our water electron dot diagram, you're going to know there's a two lone pair on oxygen because we need a octet, satisfy octet for the oxygen. There's two bonds for electrons and two lone pair for electrons, total 8 electrons. Right, because of the two lone pair, so water has is called a band structure. This angle. So we've been talking about this on previous slide. The lone pair are going to repel the bonding pairs. I mean, lone pair take more space, repel harder. I mean, more stronger repel the bonding electrons. So this angle becomes smaller. So this angle becomes squeeze a little even further from 109.5. So it becomes 104.5. So this bond is going to be more larger than 109.5. So example like water and oxygen difluoride. Those two has this kind of structure because it's two lone pair on central oxygen. In both examples, oxygen is going to be central atom. Right. So this one is not based on a tetrahedral structure. It's a no lone pair electrons on central atom. So this one electrons take further. So electrons try to repel each other as far as possible. So it's going to be on a plane. It's going to be on plane. So it's a planar structure. So this bond angle going to be 120 degree, because we know it's a full circle is 330 degree, right? Because we divide by three portion, so we got 120 degree, the bond angle 120 degree. It's called a trigonal planar because this overall structure is planar and it's triangle, so it's called trigonal planar. So examples like carbonate and the nitrate ion, carbonate ion, and SO3, BF3, all those examples. So if you draw the Lewis dot structure, you're going to know this. Like BF3, you have B, F, right? Oops. And a central atom, there's no lone pair electrons. Have three terminal, the central no lone pair is going to take a trigonal planar structure and shape. So next one is still no lone pair on central atom. So we talk about all the lone pair and no lone pair all depends all on central atom. So basically, the structure of central atom, the Lewis structure or electron dot structure of central atom, going to determine the 3D geometry of a molecule. So the center, so the electron dot diagram of central atom is very important. So now central atom, there's no lone pair. So these two bonds are going to repel each other as far as possible. So we're going to have 300 degree divided by 2. So we end up with 180 degree. This bond angle 180 degree. Because this is going to be a linear, one line on a line, so we call it a linear structure. So we have a carbon dioxide. If you recall, carbon dioxide is like a straight line, right? Because it's no lone pair electron on central carbon. Only two. There's a two-terminal oxygen, so it's a linear structure. Because it's next few slides we're going to talk about why sometimes carbon there's no lone pair, sometimes has lone pair on it, something like, right? Like mercury chloride. And just 3 examples. Right, this is a summary of electron pair geometry and geometry of molecule and the bond angle. Our lone pair substitution. No, not this one. So when you try to figure out this 3D geometry, you start with electron pair geometry. You need to figure out a central atom, this electron dot diagram of central atom first, to figure out which one is bonding pair, which one is a lone pair. Then starting from there, you can figure out this geometry. Right? Linear, when there's no lone pair, there's no lone pair, so it's a linear because there's only 2 terminal, and when it's there's three bonds going to be trigonal planar. If there's one lone pair, this molecule geometry going to be bent. When we talk about the geometry, we don't think about this lone pair, because lone pair you're not going to see it, because it's electrons much smaller. You only have 3 atoms, so it's bent. This one need 4. This one need 4 atoms. This one only 3 atoms, right? And electron pair geometry is if it's 4 bonds, going to take a tetrahedral structure. If all these 4 bonding pairs going to tetrahedral, if there's a 1 lone pair going to be trigonal pyramidal, if there's 2 lone pair, you're going to have a band structure. So this one, molecular geometry is same as this one. However, the electron pair geometry is going to be different, this two. But apparent molecular geometry is going to be same, this two. Right, if you have 5, basically 10 electrons. Remember when we talk about section 3, we talk about this expanded octet. This only happen for periodic table period 3 and beyond, and they have a d orbital. So only the period 3, but when the element has a d orbital, 3d orbital, start there, those elements can have expanded octet. So both this one, 5 and 6 is expanded octet. So if we have expanded octet, 10 electrons on the central atom, if there's a 5 terminal atoms, on the 5 bonds, going to take a trigonal bipyramidal, this kind of on the central, this is 3 terminal atom form a plane, and this one on top and the bottom, those two are perpendicular. These 2 bonds kind of perpendicular to the central plane. Because the trigonal bipyramidal is this is this one here. Trigonal pyramidal. It's kind of different. Basically, you put 2 this one is on top, one is on bottom. Basically, you have 2 this structure put at the bottom. One is on top, one is on bottom. So that's like a trigonal bipyramidal. If we have 1 lone pair substitution, it's going to be like something like that. If we have 2 lone pair, going to become T-shaped. Something like that. And just 1 lone pair out of the phase. There's another lone pair electrons at the back of the phase. So that's why something like that. So that's why it's called T-shape. If there's a 3 lone pair substitution, so then it become linear. So this one going to be same as this one. However, apparent geometry is same. However, the nature is different just because this one has 3 lone pair on central atom. This one no lone pair on central atom. Similar thing if we have 6 electron pairs, 12 electrons on central atom. If there's a 6 terminal atom, so going to be a 6 bond called an octahedral. Basically, you have tetrahedral, 2 tetrahedral, on top of each other, going to become octahedral. Basically, there's 8 phases, and it's too hard to draw. So you're going to have this simulation. You can play around with the simulation. You can know this one better. Called octahedral. This has a lone pair derivative. So 1 lone pair become 5 terminal. It's going to be something like a squared pyramidal. If you have 2 lone pair, it becomes square, basically planar square. Just on the same plane. Become same plane. One atom center. There's a 4 at a corner. You're going to have another one on top. Another atom. This become lone pair. It's a lone pair. It's a lone pair. 2 electrons, a lone pair. 1 lone pair on top, 1 lone pair on bottom. So the center become a square planar. If we have 3 lone pair electrons, it's going to become T-shape. You have if we have 4 lone pair electrons, it become linear, same as this. However, there's 4 lone pair there. So this all started with the electron configuration of a central atom. So this is the foundation. Section 3 is the foundation for this. So you really need to review section 3 if you still don't know how to figure out the electron dot diagram. Right. So there's another next concept about hybridization. So for example, we have CH4 and the CO2. So CH4 is structure going to be like this. Right. So carbon dioxide, like that. So first one, CH4 is tetrahedral, and carbon dioxide is linear. So why sometimes carbon, in both cases carbon a central atom, why sometimes carbon has a tetrahedral structure, why sometimes carbon central atom has linear structure. So how can tell the difference? So we can use the hybridization theory to explain this. So what's hybridization? It's basically the purpose of hybridization is those atomic orbitals going to mix, form new hybrid orbitals, like s and p orbital. In this example, s and p orbital going to mix together and form sp3 orbital, something like that. So the purpose is to lower the energy, lower the overall energy of system. So we could have three possibilities. So one is called sp3 in this. So this number of orbitals it's not about number of electrons, about number of orbitals. So one s orbital, three p orbitals, so mixed together form four sp3 orbitals. So basically you can tell from sp3. So s is one s orbital, p is a 3. So 3p orbitals, so total is 4 orbitals. So sp3 has 4 orbitals. sp2 is 1 plus 2, because there's 2 p orbitals. There's 1 s orbital, 2 p orbital, 2 p orbital from superscript 2. So 2 p orbital, this mixes, we got 3 sp2 orbitals. And sp orbitals 1s plus 1p. The superscript, number of superscript is number of orbitals. So 1s, 1p form this 2 sp orbitals. Okay, lone pair sometimes also take occupy this hybrid orbitals. We'll talk about later what's the lone pair, how the lone pair involve this hybrid orbitals. Because hybrid orbital only form sigma bond. Remember we talked about single bond, double bond, single bond, sigma bond, double bond, sigma plus pi bond, and the triple bond, sigma plus 2 pi bond. Right? So so sigma bond, hybrid orbital only form sigma bond. So only the sigma bond hybrid orbital. The pi bond not from hybrid orbital. So we'll talk about later where the pi bond come from. So there's a single bond, double bond, triple bond. It can only have one hybrid orbital. So double, triple, single, double, triple bond, no matter which kind of bond, there's only one hybrid orbital. We'll talk about more about this concept on following slide. Right. So we talk about sp3 hybridization. So sp3 we have 1s plus 3p. So 3 come from the superscript on p. So 3p. So we have 4 sp3 orbitals. 1s plus 3p. So 1 plus 3 is 4 sp3 orbitals. So we have 4 orbitals. So 4 orbitals, we talk about this hybridization, hybrid bonds form sigma bonds only. So 4 sp3 orbitals, 4 hybrid orbitals. So we can have 4 sigma bonds. So for sigma bond is a tetrahedral structure. So it's the geometry we talked about previously. So we have there's a 4 bond. Each bond angle is 109.5 degree. So if we have lone pair substitution, we're going to have a trigonal pyramidal or band structure. Like if we you have a lone pair substitution on this one, there's always central atom. So we have 3 at the bottom, so they become trigonal pyramidal. You have a 2 lone pair substitution, like water in water. So this is going to be band. This is 2 terminal hydrogen with central oxygen, going to be band shapes. Right, so sp2, so we have 1s plus 2p, right? So this 2 come from this superscript on p. We have 3 sp2. So it's a 3 sp2 hybrid orbitals. There's 3. So 3 sp2 can form a 3 sigma bond. So we have so this one is sigma, this one is sigma, this one is sigma. This double bond is 1 sigma plus 1 pi. We talked about this earlier section. You need to recall this one. This is double bond 1 sigma 1 pi bond. So where does pi bond come from? This pi bond comes from the p orbital perpendicular to. So if you look at this structure, so this is going to be form a plane here. So this all those are on the same plane. Everything on the red color on same plane, right? So this all the sigma bond. Right? All the red color is sigma bond, all the sigma bond. Draw this. So this is sigma bond, those are sigma bonds, sigma bonds. All the red color are sigma bond. So the pi bond comes from this. This one is perpendicular, it's 90 degree to this plane. So this one here, same, 90 degree to the plane, red color. So this is a 2p orbitals. This is a p orbital. Colors bad. So this is a p orbital here, p orbital here. This is another p orbital. This p orientation. Remember we talked about p orbital x, y, z. P orbitals are always located on x, y, z. So basically x, y, z is perpendicular to each other, right? So this is 3 p orbitals also perpendicular to each other. So on the central carbon, it's a 2p on the central carbon, right? So there's another p orbital, because we know there's 3 p orbitals, px, py, pz. Px, py, pz. This is early chapter when we talk about electron configuration, kind of electron. So there's 3p electron configuration when I talk about. So 3p orbital, there's a 2p involved in hybridization. So there's another p orbital left over from this perpendicular to the 2p from the hybrid orbital. So this one going to form a shoulder to shoulder, form a pi bond. So this is the pi bond here. This kind of shoulder to shoulder. Basically, this green color is perpendicular to the red color. So this green color, this is the blue in the image is blue color. It's perpendicular, so it's form pi bond. On top and bottom is one pi bond. Overlapping. Remember we talked about the pi bond earlier. If you forgot how the pi bond basically is one molecule p orbital. It's another molecule shoulder to shoulder from pi bond. It's not all the sigma bond head to head. Pi bond is shoulder to shoulder kind of. This orientation for pi bond. So we have a pi bond, a sigma bond, pi bond, sigma bond from hybrid bond orbitals. Pi bond from the p orbital is perpendicular to the perpendicular, above and below the atoms. So this is a sigma bond, and this is the pi bond perpendicular. This is a p orbital perpendicular to the sigma bond plane. So in this case, we have sigma bond, we have pi bond over there. Triple bond, in the triple bond case, we have one sigma bond, two pi bond. So another pi bond, I believe on next slide we talk about how the orientation of two pi bond. So so we have for sp hybridization, we have 1s plus 1p. There's a 1s, 1p. So we have two sp hybrid bond, hybrid orbitals. So make sp orbitals, there's two sp hybrid orbitals. So two hybrid orbitals form two sigma bond. Remember, we could have three p orbitals, one used in hybridization. So we have another leftovers, two p orbitals. It's two p orbitals. Two p orbitals perpendicular, orientation perpendicular. The same thing at px, py, pz, x, y, z, three axes perpendicular to each other. So if we take this one at x, this one as a y-axis, so this one going to be z-axis. So x, y, z going to three-dimensional is going to be perpendicular to each other. So if sigma bonds along x-axis, and the other two p orbital is another p along this y-axis, another p orbital along z orbital, something like that. So the other two p orbital going to perpendicular to each other, also perpendicular to sigma bond. So we have one sigma bond, one triple bond. There's two p orbital, two pi bond. So two pi bonds, orientation of this two pi bond going to perpendicular to each other, also perpendicular to sigma bond. So basically, think about sigma along x, and the other two pi bonds are going to be, going to kind of along the y and z axis. So the example is carbon dioxide, kind of like that. Carbon have one sigma bond, one pi bond, another pi bond here. Right? So remember we talked about single bond, double bond, triple bond. No matter what, there's only one sigma bond, one sigma bond, one sigma bond. Everything else is multiple bond. This is a pi bond. This is 2 pi bond for triple bond. So this is double bond is 1 sigma plus 1 pi. This double bond 1 sigma plus 1 pi. So we can have this sigma bond. Then we have pi bond. So the other 2 pi bonds, this pi bond here. Then the other pi bond going to be perpendicular to this pi bond. So this pi here, the other pi, if you see the orientation, so here's perpendicular between this going to be perpendicular, and perpendicular between this and this sigma bond perpendicular. So basically it's X, Y, and Z. Okay? So this 2 pi bond going to be perpendicular to each other. This pi. So angle perpendicular to each other. This 2 pi bond. So same thing for nitrogen gas. Nitrogen gas is a triple bond in the middle. So this is a sigma bond. And the other ones, for example, if this Y, the other is Z. So this one here form a pi bond along the Z here. Another Z, so the other pi bond. Right. So here's the examples how to figure out the geometry starting from name from the name of compound to figure out the geometry. So this basically linked from name you need to figure out the formula, and from formula you need to figure out electron dot diagram, and from electron dot diagram can figure out a molecular shape. So basically you need to from name to figure out a formula. Then for formula, you need to figure out electron dot diagram. And from electron dot diagram, you figure out the molecular shape. Right? Blah blah blah. The colorless gas and whatever, fish, flash, or whatever. So we need to figure out the shape of molecule, predict bond angle, and hybrid orbitals. Right? So first thing, figure out the formula, the name, phosphorus trihydride. So the formula going to be phosphorus trihydride. Basically, tri 3 means 3, hydride, hydrogen, pH 3. Then we figure out the electron dot diagram. From electron dot diagram, figure out the shape. Oops. Right. So first thing, figure out the number of valence electron total. Phosphorus have 5 valence electrons, hydrogen have 1 valence electron, total 8 valence electrons. So 8 valence electron, 4 pairs. So you put these 4 pairs around central phosphorus, it's going to be a 1 lone pair with 3 bonds. It's 4 pair, 4 valence 4 pair 8 valence electron, 4 pair 8 electrons. So the molecular shape is going to be something like that. This kind of derived of tetrahedral. Tetrahedral is if you have a full. So basically it says have 4 pairs of electrons. It's tetrahedral. However, there's a lone pair. Lone pair, not going to see it. we're not going to see it. So there's a molecular. When I think about the molecular geometry, you don't need to worry about lone pair. So basically, 3-terminal hydrogen. So it's a kind of a trigonal pyramidal structure called. And remember we talked about the tetrahedral. Perfect tetrahedral is 109.5 degree. 109.5 degree. However, this lone pair, remember we talked about lone pair take more space. Lone pair are going to repel this bonding pair more. So this kind of squeeze the hydrogen pH bond together. So this bond angle becomes smaller than 109.5. So in this case, it becomes 17 degree. So the geometry is trigonal pyramidal, and the bond angle is smaller. You don't need to predict the exact number, just smaller than 109.5. It should be good. Right? Basically, that's all for this section. So we talk about two ideas, two theories, kind of relate to each other. Whisper surveillance shell electron pair repulsion theory. So the idea is the electron pair is going to repel each other, try to move away from each other as far as possible. Hybridization gives us the nature of sigma bonds, pi bonds. We have sp could have sp, sp2, sp3, right? So sp3 is 4 orbitals, basically 4 sigma bond. Here is 1 plus 2, 3 sigma bond. This one has 2 sigma bond. Right, that's all for section 4.